So
Oh,
thanks for.
let me introduce you.
Oh, I see. Okay, go ahead.
So we're delighted to have Tony Bloch back for the second of the two seminars. And to remind you from the last time, so Anthony Bloch is the Alexander Ziwet Collegiate Professor of Mathematics at the University of Michigan, where he has served as Graduate Department Chair. He received a BSc honors in Applied Mathematics and Physics from the University of Witwatersrand in Johannesburg in 1978, an MS in Physics from Caltech in 1979, an MPhil in Control Theory and Operations Research from Cambridge in 1981, and a PhD in Applied Mathematics from a little place people have not heard of, Harvard, in 1985. Main research interests are in dynamics, differential equations, and control. He has received various awards, including a prestigious Young Investigator Award, the Guggenheim Fellowship, and a Simons Fellowship, and is a fellow of the American Mathematical Society, the Institute of Electrical and Electronics Engineers, and the Society for Industrial and Applied Mathematics. He was a senior fellow of the Michigan Society of Fellows and a member of the Institute for Advanced Studies. He was editor-in-chief of the SIAM Journal of Control and Optimization and is currently editor-in-chief of the Journal of Nonlinear Science, as well as series editor for Springer Applied Mathematics. Just an unbelievable brief CV. We're really honored to have you. Thank you so much for taking the time, and please take it away when you're ready.
Great. Well, thank you for the introduction, and thanks again for the invitation to talk. So I want to continue with what I was discussing last time. So I'm going to sort of embellish various things that I discussed. So so this is mainly non-holonomic mechanics, but I'll talk about some related things in mechanics in general. And as last time, feel free to ask questions as I go along. So I'm going to say something about Hamiltonian and Poisson systems. So non-holonomic systems are almost Poisson, but not Poisson. I'll explain that. I'll say something about the difference between variational non-holonomic systems, which we were just discussing, which are sometimes called vacuonomic systems, and non-holonomic or Lagrange-D'Alembert type systems. There's a particular form of the equations of motion that are fun to look at called the Euler-Poincare Suslov equations, which are interesting just for their dynamics and which are occasionally integrable. And finally, I'll say something about a way of formulating the non-holonomic mechanics. That's through Hamel's equations, going back to some classical formulations of mechanical systems in general. And depending on the time, I'll say a little bit about how one might quantize such systems or not, and also how one might generalize these things to infinite dimensional systems. So let me remind you a little bit about Poisson or almost Poisson systems. So basically, as we know in mechanics, one often wants to write down a bracket which describes the dynamics, the classical Poisson bracket and its variations, which are useful in lots of ways, and particularly for quantizing. But non-holonomic systems are actually never Hamiltonian, and that's related to the interesting properties that they have, such as asymptotic stability, non-conservation of volume in certain cases. So one thing that they do have, though, is this almost Poisson structure. So basically what an almost Poisson structure is, it's a Poisson bracket which doesn't satisfy the Jacobi identity. So it's still skew. And the important thing about that is skewness means that energy is preserved. So in the absence of external dissipation, energy is still preserved for non-holonomic systems, but volume is not. And that is reflected by the fact that the Jacobi identity is not satisfied. And that's key to satisfying volume preservation for Hamiltonian systems. And you can show basically that there's this notion called the Jacobiator. That's really the sum of the terms that would be the Jacobi identity being equal to zero normally, but it doesn't vanish in general. So the Jacobiator was coined by Alan Weinstein, who was looking at almost Poisson systems in general, just for abstract reasons, but it's important for non-holonomic systems. So for a non-holonomic system, this Jacobiator, the sum of f, g, bracket h, and so on, does not vanish. So you can define an almost Poisson vector field. So you take the Poisson tensor. So if it was a regular Hamiltonian system, you just have z dot equals j grad h, where j is I minus I. For a non-holonomic system, you have some more general thing where it isn't actually a Poisson tensor. So, so let me just say a little bit for those of you who know, I'm not going to say too much about this here, but so something about Poisson structures. So Poisson structures often come from symplectic structures. They're a little more general. So if P is a manifold and omega is a two-form, this is a symplectic structure. if it's non-degenerate, so it's a two form, it's skew, it's non-degenerate, and its differential is equal to zero. D omega is equal to zero. And again, sort of in the Poisson context, the important thing, omega is skew, again, means you get Hamiltonian as opposed to gradient or something else. And the fact that it's closed is really equivalent to having the Jacobi identity satisfied. So d omega equal to zero means the Jacobi identity is satisfied, that volume is preserved, and that's the characteristic of Hamiltonian systems, though, as I said, in general, not for non-holonomic systems, although you can manipulate in the various ways. You can change the time. There are ways of sort of getting at a Hamiltonian system change of time. I won't mention too much about that here. Also, you can reduce it to a low dimensional system, which is sometimes Hamiltonian. I will say something about that. And in any case, so if you have a symplectic manifold, it's called a P omega. If I give you a Hamiltonian, I can define for you the Hamiltonian vector field through this relationship 17 here, omega of xfv equals df dot v. So I give you the f, and from this relationship, I can get the Hamiltonian vector field. And you can do a similar thing, in the almost setting for non-holonomic systems. And again, in the symplectic context, you can define the Poisson bracket, and that's just given by f bracket g equals omega, the skew symmetric form acting on the corresponding vector fields x sub f and x sub g. And then you have a Poisson manifold. So every symplectic manifold is Poisson, but the reverse is not true, and that's important in a lot of different ways in mechanics, in particular the rigid body equations, which I discussed last time. And the key thing there is you have a Poisson bracket, which is degenerate. It has a Casimir, a quantity that commutes with all other functions. And for the rigid body, that's the momentum, or the total angular momentum. And these give rise to what are called in general the Euler-Poincare equations. And in the non-holonomic setting, these are the Euler-Poincare Suslov equations, which I mentioned earlier. So you can put constraints on a Lie-Poisson system. And the important thing, of course, in mechanics is that if the system is given by the canonical Poisson, or canonical Poisson bracket, or canonical form sigma dqi wedge dpi, you get the canonical Hamiltonian equations. And more generally, you get something like the rigid body equations if it's Poisson. And there's also a sort of an analogous form, again, due to Alan Weinstein, which tells you if you have an almost Poisson bracket, you can get something that's similar, but with a bunch of zeros floating around as well. So that's that. So the Lie-Poisson bracket is the thing that we're interested in for rigid body type systems. So one doesn't have to have the canonical bracket. You can have other brackets. The Lie-Poisson bracket is this bracket here. And the way you can think about it is mu here is actually, say, for the rigid body is the momentum. And what you do is you pair the total momentum with the bracket of the derivatives of the functions with respect to momentum. And that sort of generalizes to an arbitrary Lie algebra. And it's a kind of beautiful bracket, which plays a role in some of the discussions that I'll have later on in this talk. And you can write it down quite explicitly. So that's the general form. If you know what the Lie algebra is, if it's a finite dimensional Lie algebra, the coordinates psi1 through to psi-m, and dual coordinates g star mu1 through to mu-m, which I again think of as the momentum, you can write it down quite explicitly in terms of the structure constants of the Lie algebra. So you have this very explicit form, which reduces, for example, to the rigid body equation or the rigid body bracket on SO3, but you can do it for any reasonable Lie algebra. So that's the sort of theoretical background. So let me just say, let me go back to the rigid body, and later on I'll talk about the constrained rigid body and other things related to sort of bracket things that look like this. So as we did last time, you can look at the Euler equations of motion for rigid body dynamics. They're just pi dot equals pi cross omega. And to get back to the sort of Lie algebra formulation, one normally has this sort of hat map. If you can think of omega as a vector, but you can actually map it to matrices little SO3. So I could just as well write it as pi hat equals pi hat cross omega hat, where those are the corresponding elements of SO3. So pi I omega equals I omega here is the body angular momentum. Omega is the body angular velocity. And these equations are Hamiltonian with respect to a Lie-Poisson structure again. And this is the very explicit form of what I just wrote earlier. So in this case, the bracket is just pi dot grad f cross grad k for two functions f and k. And you have a minus sign for left invariant and a plus sign for right invariant rigid body equations. So those are the equations of motion. And as we know, the energy, of course, is conserved. It looks like pi dot equals I to the pi dot I to the minus 1 pi. And I can write the equations in this Poisson bracket form. So those are Euler's equations written as a Poisson bracket. And as I said, the key thing about Lie-Poisson brackets or brackets of rigid body types is that the brackets are degenerate, which means that there's a function, which I'll call a Casimir, which commutes with all the other functions. So this is a property of the bracket, not the system. So just because I have a degenerate bracket, there's something that commutes with everything. But of course, in particular, it commutes with the Hamiltonian. And so it naturally gives you a conservation law. So if I take any Hamiltonian whatsoever, not necessarily the rigid body Hamiltonian, I'll get a conservation law just from the bracket. And in this case, for the rigid body bracket, it's just the norm of the total angular momentum squared or any function of it. And you can check that that commutes with anything. And that gives you this nice momentum sphere for the rigid body that we discussed last time. So the rigid body equations evolve on a momentum sphere. And if it's a higher dimensional bracket, you might have other Casimirs as well. And these play an important role, both in the geometry of system, but also in the stability. There's something we call the energy Casimir method. So if you want to prove stability, for example, you want a Lyapunov function, and often you might take that as a combination of the energy plus these Casimirs, and more generally other conserved quantities. That's the Casimir. And as I said, you can generalize this in various ways, in particular to these Hamel's equations. I'll come back to that, where you write things in terms of quasi-velocities. And just as a preview of that, of course, the pi, the angular velocity for the rigid body, is not really the derivative of any particular coordinate. That's why we call it a quasi-velocity. It's some sort of weird combination of the Euler angles, if you like. And that's sort of important in non-holonomic systems in general. Okay. And then, of course, the other structure that you want on a manifold is its Riemannian structure. So you have a Hamiltonian. Any reasonable manifold also has a Riemannian structure, which gives you a metric on the system, and that enables you to look at the geodesic flow, and the rigid body equations, of course, are in some sense the geodesic flow on SO3. And also, given a metric, you can look at the gradient vector field as opposed to the Hamiltonian. And the interesting thing about non-holonomic systems and some Hamiltonian systems is that they sometimes have gradient-like properties as well as Hamiltonian. So that's one of the things that makes them interesting. The other thing, sort of abstract thing I just want to mention is control systems. As I mentioned earlier, I want to relate these to control systems. So I can give you any differential equation. We write it normally as x dot equals f of x. So what is a control system? A control system is where you have an external input, which I call u of t. You can think of it as an external force, or it could just be a change of velocity. Basically, it's just a time-dependent map. And the point is, the system it depends on x, but now you can try and get the system to behave in some nice way by changing u. So that's control problems. And u is generally chosen to be quite general, it could be piecewise smooth or piecewise analytic. And the idea with a control system like this is you want the system you don't only want to observe the system, you want to try and change its behavior. So for the rigid body, for example, you might want to change it to spin about another axis if it's spinning about a given axis. And in general, for a system, the two basic control problems are trying to move it from one point in the phase space to another, or trying to stabilize an unstable equilibrium. So, for example, as I mentioned last time, the rigid body is unstable about its middle axis. It spins unstably about the middle axis, but stably about the major or minor axes. And you can choose a control, if you do it the right way, to make it spin stably about the middle axis. And that was something I worked on. It's a nice sort of example. There are a couple of papers I wrote with Jerry Marsden on that, where you can sort of use the Casimirs. You change the Hamiltonian structure, you change the Casimirs with the control, and you can change the way it sort of rotates. So it's kind of a fun thing to look at actually. Anyway, so there are lots of examples. That's quite general. And you can also look at the optimal control problem, which means you want to move it, optimally from one point to another. It might be minimizing the time, minimizing some other function like the metric. And that's really important. And it relates to this variational or Wackonomic mechanics that I'll come to in a moment. So I want to illustrate all of these things with some examples. Let me go back to the vertical disk, which is nice for illustrating both the dynamics for non-holonomic systems as well as control. So just to remind you from last time, here's my rolling disk. In some sense, a very sort of canonical non-holonomic system. It rolls around in the plane. Its position is x, y. It has two angle coordinates, theta and phi. Theta gives you the amount of roll. Phi gives you the angle that it makes with the x-axis, for example. And so you can think of this as just observing the problem, and you also might want to try and control it. So this is the sort of non-holonomic version without controls. I have the kinetic energy, which is just the sum of the free particle kinetic energies of each coordinate. And I have these non-holonomic constraints of rolling without slipping. So d theta changes, and so do dx and dy. So it rolls but doesn't slip. And you can think of it as a system, a sort of free system, if you like, but you could also add controls. And the interesting thing is that, the way you can enforce the constraints is similar to the way the controls enter it. So the way you think of it as a controlled non-holonomic system is the following. So these are essentially the Lagrange-D'Alembert equations. I have d by dt equals dl dq dot. That's really all I have from the Lagrangian because there's no potential. And then on the right-hand side of this equation, I've put Lagrange multipliers lambda 1 and lambda 2, which enforce the constraints. So there's constraints at the bottom of the page here. And then in addition, I could add in these controls, and I can think of the controls I want to think about are like steering a car. They're the controls of rolling and turning. So there's one control that changes the theta variable. There's another control which changes phi. So I roll and I steer, and at the same time I have to enforce the constraints through Lagrange multipliers, and you can think of those as being the forces of constraint. And so W1 and W2 give you the direction of the forces of constraint, and lambda 1 and lambda 2 gives you their magnitude. And what you can always do in these systems, you can eliminate the multipliers, lambda 1 and lambda 2. So you append it to the constraint. So I have these constraint equations as well. You fiddle around a little bit. You can eliminate the constraints, and you can reduce the dynamics to dynamics on what I'd call the base space, which is theta and phi. And I'll come back to that picture in a moment. It's related to this little fiber bundle picture that I discussed last time. So in the base space in theta and phi, I have second order equations, and so you can think of this as being just F equals ma, if you like, on the base space. And what you see here is that it's Hamiltonian on the base space. This is just F equals ma. It's naturally Hamiltonian, but the full system is not. But basically, you can get the dynamics now just by solving for these equations for any u you like, and then you can construct the dynamics in x and y using the constraints. And in the free case, of course, if u1 equals u2 equals 0, you can obviously integrate the equation. So this is integrable in a sort of trivial way. We'll look at more non-trivial integrable non-holonomic systems later. And the other interesting thing, I mean, it's simple here, but it's kind of important, is if you look at the second equation, j phi double dot, if u2 is equal to 0, j phi double dot equals 0. So that just corresponds to conservation of angular momentum, which is just spinning about the vertical axes. Of course, if u1 is equal to 0, you also get theta double dot equals 0 on the left-hand side, but that's sort of non-trivial in the sense that the moment of inertia is modified by mr squared. That comes from the constraints. So one of them corresponds to kind of a free motion and the other not. And this is related to what I'll discuss later about the so-called momentum equation. So the bottom equation is sort of standard Noether's theorem, conservation of angular momentum. The top equation is an instance of a more complicated momentum equation. Okay. And as I said, you can think of this as a kind of in a kind of geometrical way. If I think so, the controls are U1 and U2. The variables theta and phi I think of as base variables in a fiber bundle. I'll come back to that. And so so the way you can think of the system is I change theta and phi using the variables U1 and U2 in this base, and then the variables x and y are in the fiber, and I want to try and change x and y in the fiber by indirectly, at least indirectly changing theta and phi. And as I mentioned last time, it's clear that the system is controllable in the base. I can move it around any way I like. But the interesting thing as well is it's fully controllable. By choosing theta and phi in the right way, I can actually manipulate the system in the full phase space. And that's because of the non-holonomic nature of the system. If it was holonomic, I'd have a constraint on the variables. And of course, that would constrain me to some subregion of the configuration space. But since it's non-holonomic, in fact, the non-holonomic constraints help me. And that's sort of one of the lessons of all of this is that if you have non-holonomic constraints and plus controls, often the system is more controllable. So non-holonomic constraints are actually good constraints if you're interested in control. And one other thing that I'll come back to is that you can also think of what's called the kinematic control. So if you look at a lot of engineering, in fact, people look at what are called kinematic systems, so you don't really worry about the dynamics. So you could actually just forget about the dynamics in some sense, in this case means forgetting about the Lagrangian, and you just think about moving the system around in the configurations, or at least in the phase space, subject to the constraints. So you think of the constraints as describing a distribution, and what does a distribution mean? It means you can only move in certain directions in the tangent space. You're constrained to, in this case, a two-dimensional subspace of the tangent space. And so this kinematic system is just this one that I've written here in terms of x1 bar and x2 bar. And these are just a maximal set of vector fields on the configuration space satisfying the constraints. So you're just moving around in the phase space, if you like, subject to these constraints and not worrying about the dynamics. And that's, for example, people use that in robotic path planning, for example. If I have a bunch of obstacles, I just want to know if I can move it around in a certain way. And if it's slow enough, I don't actually care about the dynamics. So these kinematic systems are kind of beautiful in their own way, actually. And often people in nonlinear control, when they talk about a non-holonomic system, this is what they mean, a kinematic one rather than a dynamic one. Okay, so I want to say something about optimal and then vaconomic. So otherwise, any questions so far? Okay, so let's just think about the optimal steering problem. So this is also nice. So let's suppose that I want to move something from one. So I could do it with a disk, but I'm going to do it with a little simpler case. Suppose I want to steer a system starting at a time t equals 0 to another point. All right, so an optimal steering problem might be something like this. I want to minimize the integral x dot squared plus y dot squared among all curves joining 2 points, say from 0, 0, 0 to 0, 0, a, just as an example, and satisfying a constraint. And this, as you'll see, is related to vaconomic problems. So if I want to do an optimal path, I want to minimize, say, x dot squared plus y dot squared, and this is like a what we call a sub-Riemannian metric. It could, if you're in 3 space, you'd have x dot squared plus y dot squared plus z dot squared as a full metric. This is so-called sub-Riemannian. One direction is 0. And let's suppose we have a constraint, z dot equals yx dot minus xy dot. And again, you want to satisfy the Euler-Lagrange equations. But since that I'm just doing optimal control as opposed to non-holonomic, I can just append the constraint to the Lagrangian, which in this case is x dot squared plus y dot squared, and see what dynamics I get. And in this case, the corresponding Euler-Lagrange equations of this system are the ones I give in here, x double dot plus y double dot, and an equation for lambda dot, which depend on time as well. And this, in fact, is the z dot equation. So if you look at these equations, the top 2 equations correspond to the regular d by dt dl by dx dot, but of course I have no z dot here, so I don't get a z dot. But of course you can actually solve this. This tells you that lambda is a constant. I can actually solve this quite explicitly. and I get a trajectory that looks like this. This is the optimal control trajectory. So the one you should look at is the red equation. So basically what this tells me is that if I want to get, say, from 0, 0, 0 to 0, 0, A, I take a kind of a kind of twisting path. So if you project it down to the XY plane, it's a circle, but otherwise you're just winding around up across a cylinder. Okay, so this is the optimal path that gets you from 0, 0, 0 to 0, 0, A. And in fact, you can check that you can't sort of go directly up the x-axis. So this is sort of the optimal steering problem, which gets you from the point 0, 0, 0 to 0, 0, A subject to this constraint. And that's an example of a vacuonomic problem. I'll come back to that.
Do you get a solution for, so you said lambda is a constant, do you get a different solution for different constants, or is that constant somehow fixed?
Yeah, so that would depend, right? So that so then it's actually it's like a 2-point boundary value problem. So in fact, yeah, so you get different lambda depending on where you start and where you end up. But of course, in general, lambda is not constant. It just happens to be in this case, which is a particularly nice example. But it does depend on the boundary conditions. And just like, Lagrange, optimal control, just like, Lagrangian mechanics is really a 2-point boundary value problem. So here's another fun example to think of, which I won't go into example here, but this is a more complicated optimal control or optimal control problem. Suppose you have a ball in the plane and you want to steer it from one point to another. Well, one interesting way to do this is to have a couple of rotors inside it, and people have actually constructed robots that are like this. So you have two little rotors. You spin the rotors up, and if you spin them back and forth, you can get this ball to roll around in the plane, and you can do interesting sort of control or optimal control problems using that as well. So just to say a little more about the geometry, so this applies both to this optimal control problem I just discussed and to the rolling penny. So the way you think about it, as I said, is you kind of have a bundle structure, and it also applies, to the Elroy's beanie problem I mentioned last time, where the base space is sort of the internal angle, and also to this problem that I just showed you. So where you think of the wheels as sort of turning around, being the internal angle. And so the idea is you have a base space. So for the rolling penny, the base space was the theta and phi's. And what you wanted to do was move it around in x and y space. So this is sort of reminiscent of fiber bundles in geometry, and that's the way we think of it quite explicitly. So you think of yourself moving in this base space, the variables say you can control theta and phi. You move around in theta and phi, and then you actually can move yourself around in x and y, similar to that optimal control problem that I just showed you. So this sort of picture is what you should think about when you have both non-holonomic systems in general. So in the non-holonomic setting, you're relating base variables to fiber variables via the non-holonomic constraints. Or if you have control systems where you think of yourself having sort of direct control over things in the base space and you want to move around in the fiber. So that's kind of a nice thing. And you can, of course, write a very precise general definition of this, but this is the picture. So you're moving around in the base and you want to get yourself around in the fiber. And this is related to a whole lot of interesting things. So we're talking about non-holonomic mechanics. If you move around in the base, that's an example of if you change in the fiber, that's an example of what people call holonomy, and people in physics often call that holonomy. And it's also related to this famous Berry's phase in quantum mechanics, for example. So here are some just examples. So this is the phase. I won't say too much about this, but you can think about it as just moving around on the sphere, and you can look at where the sort of if you move around on a non-trivial path in the sphere, and you have your thumb or something pointed outwards, you're going to get a non-trivial change in your thumb when you moved around a path in the sphere. And that's just kind of similar thing. So that's in that case, it's related to the curvature of the sphere, and there's a connection associated with that. And in these non-holonomic systems that we're thinking about, there's a curvature of the connection which is given by the non-holonomic constraints, which gives you a similar sort of non-trivial change. So, and this, as I mentioned here, it's also often related, this is often what's called the geometric phase. There's a phase shift between the beginning and the end of the path. And that applies in general if you have a non-trivial holonomy or you have these non-holonomic constraints. So it's related to geometric phases. And again, as I said, that's an example of what's sometimes called the Berry's phase. So in this case, as I said, you can think of the base space as the control space. And this is often thought about, this is really often thought about in locomotion problems in mechanics, for example. Another way to think about it is even if you have a walking robot or a wheeled robot where there's some sort of motion internally, you have that geometrical motion in the control space, and then you move. Another example is the skateboard that I mentioned last time. You know, so if you have that skateboard, you move your feet. That's the sort of internal motion in the base, and then you slide along, and that sliding along is motion in the fiber.
Okay, let me just ask a quick question here for sorting myself out. So I would have traditionally thought about base space as configuration space, and then the fiber bundle. Well, okay, and then you look at the tangent bundle as the natural thing to do. You're going in a different direction here.
Right. Yeah.
You're projecting this out in a different way. Any guidance on how you set this up in general, or is this more problem specific?
Yeah. So this is so this is slightly different than that, but yeah, I mean what you said is perfectly correct. So normally when you're thinking about mechanics, like what I'm just about to say, you think of the tangent bundle, right? So in the tangent bundle, the base space is the configuration space, and then the velocities are the tangent space. But in this case, we're thinking about we sort of divide the configuration space into two pieces as well, actually. So it's a different use of the connection and the fiber bundle. It's just a different fiber bundle where the base is described by these these variables x and y and are related. So what you're doing in this case is you're relating the velocities in the base space to the velocities in the fiber by a different sort of connection. So this is kind of a more general form, and so the tangent space version is just a special case of what we're thinking about. So this is what's called an error. So this is a general fiber bundle. The non-holonomic constraints describe what are called an Ehresmann connection, and it's just a generalization of the tangent space thing. So yeah, what you did is absolutely correct, just a different point of view. And so I'll say more about that. You'll see what I'm going to say in a moment. So yeah, I mean that's a good question. But yeah, so it does take a little bit of getting used to. So anyway, so going back to Hamilton's principle, so here is the Hamilton's equation that we discussed last time. And so since people asked, so what you do for Hamilton's principle, and I want to relate it again to Lagrange d'Alembert, is you have these equations of motion, these delta Qs in general, in the Lagrangian case are independent. In our case, they may not be, and that's in the case for non-holonomic systems. But the delta Qs, again, you just take variations, and that means you vary the path. So Q goes to Q of T epsilon, and you look at all possible paths with fixed endpoints, right? So you have a path Q of T epsilon, you vary it. Q of T0 is Q of T, Q of A epsilon is QA. Oh, sorry, Q of T, should this be Q0? You take variations and you get Hamilton's equations. And the contrast is with the non-holonomic case is that those variations depend on one another, and they're related by these non-holonomic constraints. And so you can think of these as, so they're written in terms of velocities, but you can also think of it as relating the deltas, and you can also think of it as relating DSs. So these constraints are not, these deltas and velocities are not independent. And this is where the sort of split that I just discussed comes in. You can write, you think of the QIs as written as two sets of variables, RAs in the base, SAs in the fiber. So what I've written them as alphas and A's. So I divide it as R alpha and SA, and I write those constraints. So the Lagrange d'Alembert equations of motion is, again, I do exactly the same sort of thing. I vary over all paths, and in addition, I have the condition that the variations satisfy these constraints. So that's Lagrange-D'Alembert. And the important thing is that you impose the variations before imposing the constraints. So I take all possible curves, do the variations, add these things in, and then I get these equations of motion, which I showed briefly last time. So the delta Q's depend on one another. I substitute in this relationship, delta SA plus AA alpha, delta R alpha equal to 0. And you can think, for example, for the penny, it was a relationship between theta and phi, and or at least between dx and theta and phi. So I had something like dx plus something cosine phi d theta and so on. I substitute it in these equations. I use the constraint equations, and I can rewrite it in terms of a constrained Lagrangian, substituting into the Lagrangian, which it's okay to do after you've done the variations, but not before. And I end up with this set of equations here, which depends on this curvature of this connection. So this is sort of what I was describing. So this connection here is what's called the Ehresmann connection between the base and the fiber. And those are those variables between the thetas and the xy's and the thetas and phi's for the penny. And I end up with this equation which depends on this curvature. And the interesting thing also is this curvature is it's a very cool object. It's the curvature of this Ehresmann connection, but in particular, it's 0 if and only if the constraints are holonomic. So if I had a holonomic, a position constraint, this curvature term would vanish, and I get the regular Hamiltonian equations.
Just a quick follow-up. What about integrable non-holonomic constraints?
Yeah, so if it's integrable, right? So again, if it's integral, so yeah, if it's integrable, then it would also vanish, right? If it's completely integrable or parts of it, the parts of the curvature would vanish. Yeah.
Which sense of integrable are we talking right now?
Yeah, so that would be a case of if the distribution is integrable. Yeah, so I'll come back to that, right? So yeah, so sorry, it is a bit confusing. So if the distribution is integrable, it's holonomic, this vanishes. If the system is solvable in the sense of an integrable system, then it's still not it still doesn't vanish, but you can actually solve it. So
okay, yeah,
is that clear?
I think we're getting there.
Yeah, I don't know. It's unfortunate. It's unfortunate nomenclature, I guess. Anyway,
you mentioned that you impose the variations before imposing the constraints.
Yeah.
What exactly do you mean by that?
So yeah, so the point is so this is what I'm just going to compare the two procedures right here. So if you impose the variation, if you do all the variations before imposing the constraints, it's consistent with Lagrange-D'Alembert and with Newton's law. If you do not, if you do the other way around, which is like that optimal control problem, it's not actually. You can just check that, and let me just show you that. All right. So if you do the reverse, so this is where we get to vaconomic. So so as I said here, the dynamic Lagrange-D'Alembert, you impose the constraints only on the variations. In variational mechanics or variational dynamics, I impose the constraints on the velocity vectors of the class of allowable curves. So what would we do if we did that? So this is a bit similar to this optimal control problem. So suppose I try to do the rolling penny by imposing constraints on the curves. So what that means is you take the Lagrangian and you put multipliers into the Lagrangian. And if you put them into the Lagrangian as opposed to imposing them later on, that's constraining the class of curves. And then you just do the same optimization problem that I mentioned earlier, and I get these set of equations here, which are in fact different ones than the ones I showed you earlier because it depends on these mu1 dots and mu2 dots. So remember the lambda before appeared pretty simply. Now I actually have a dynamic equation for the mu's, and I end up with, if I can try and do the same reduction as before, and I end up with a much more complicated set of equations. And so so before, remember, we just had the U1 and U2. Now we have all this extra stuff from the phi's and phi dots and so on. So you end up with something completely different, but these are really variational. So these are the vaconomic equations for the penny, which I claim are not physical. And on the other hand, they are good, say, for doing optimal control problems where you're trying to minimize, say, some control cost subject to certain dynamics. So does that help answer your question? I'll say a little bit more about
But you're saying that you're imposing the constraints by putting the Lagrange multipliers in, and then you're also allowing the variations to go in any direction, basically, and that's why you get the wrong answer, because your variations are not being consistent with your constraints.
Well, right. Almost. I mean, so the point is you're making the curves obey the constraints as well. You see, so you're taking so in this particular case you're taking variations over a restricted class of curves. That's the calculus of variations. In the non-holonomic case, you're taking variations over all curves, but imposing constraints on the variations after you've taken them, after you've done the variational problem. Make sense?
Yeah.
Yeah. Okay. So you can say a lot more about variations. So there's a lot of work out there. I don't want to go into all the details. I'm just going to run out of time. But so there's another paper I wrote with a graduate student I had called Jared Maruskin, and again Jerry Mars and Dmitry Zenkov, where we look at all these different variational principles. So you can say a lot more. And in particular, people asked last time about this, whether the operations of time differentiation and taking variations commute. And so in this case, they do. So taking variations, taking derivatives, in fact, commute in this setting. But in fact, depending on how you set it up, sometimes they don't. So as I mentioned here, so if you look at the you can, as I said, you can compare these Lagrange d'Alembert and these Vaconomic variations. So in the former case, as I said, the curves that define a variation fail to satisfy the constraints, while the virtual displacements belong to the constraint distribution. So that's what I just said, basically. And in the latter case, the variational curves, the curves satisfy the constraints, but the variational fields do not. That's another way of looking at it. And that sort of tells you something about how the derivatives and the variations commute. And there is an alternative definition of variations that can be found in the work of Appel and Suslov, which requires that the variations of the functions that define the constraint equals 0, and the configurations satisfy the constraint. So that's like Lagrange d'Alembert. And in that case, you get a whole lot of weird stuff that happens. And this leads, for example, I won't go through all the details here, but you have to define the velocity along the curves in a kind of non-intuitive way. And in fact, this leads to the fact that the operations of time differentiation and taking variations become non-commuting. This is related to what's called the transpositional relationships. So you can, as a twist on what I just said, you can sort of vary over all the curves, but then you have to be really careful about what the variations mean, and it leads to a sort of complicated way of doing the dynamics, where, as I said, the time derivatives don't commute with the variations, and you can still come up with the right thing, but it's kind of complicated. Yeah, so here are a couple of other things. So this again is the falling disk, which, as I said, falls under gravity. It is also solvable. You get a much more complicated Lagrangian, but much of what I just said still applies. And this is the, like the supermarket cart or the Chaplin Slayer. I'm going to say more about this in a moment. So this system exactly exemplifies what I said earlier, that the Hamiltonian is preserved, but the volume is not preserved at the phase space, since you get asymptotic stability to a given motion. And these examples here, let's see, like the rattleback top, again, sort of moves in one direction nicely and not in the other. And again, this sort of captures this non-Hamiltonian nature of the problem. And again, if you did the variational mechanic version of it, you'll end up with the wrong thing. And another example that I mentioned last time, right, was the ball on the rotating turntable. So if you did the true non-holonomic mechanics, it tells you the ball rotates it moves around on the turntable, but never falls off. But if you did the Vaconomic version, it would fly off into space. So you can actually check sort of physically or by experiment that that the non-holonomic is correct, but the variational non-holonomic or Vaconomic is not correct. So let me say, so that's something about the mechanics and so on. So I want to say more about the dynamics, integrable, not integrable, what things look like. So again, let's go back to the Chaplin Slay. So this is sort of the most trivial, the simplest example in a way that exhibits dynamics that really isn't Hamiltonian. with one exception. So this is the Slay equations. They are also related to the total lattice, which I showed you last time. So here's the Slay. It's got this rather beautiful dynamics. So again, you want to reduce it just like I did for the penny to the velocities. So you can write it down in terms of the angles, but you can reduce it to these equations here. So V is the velocity, and this is related to quasi-velocities like the rigid body. So V is the velocity along the line, sort of along the line between the contact point and the center of mass, and omega is just the angular velocity about the center of mass. So these are the equations. So V dot equals A omega squared, and omega dot equals this expression times V omega. So it's quadratic on the right-hand side. You can check it has a family of relative equilibria. So for example, if you put omega equal to 0, it's clearly 0. And linearizing about any of these equilibria, you find you get one zero eigenvalue and one negative eigenvalue. And as I say here, the solution curves are ellipses in the VW plane, the V omega plane, with a positive V-axis attracting all solutions. So if you just get rid of the constants, it's just the set of equations here. You can check, in fact, this relates to the total lattice equations, which is for particle dynamics. So this is one interesting case where it has a sort of Hamiltonian structure. But in fact, you have to restrict the sign a little bit, and that's really important. But in fact, they're interesting things. People have asked me about this. You can write it in Lax pair form. It is integrable. It can be solved by the method of factorization, and the solutions, in fact, in the end are tangents and cinches. But this is the phase portrait, and you can see that it has this asymptotic behavior. So if you start in any of these points, you'll move around here to the z-axis, or to the y-axis here. And the point is, it's really, you can see it's non-Hamiltonian in lots of different ways. First of all, it has asymptotic stability to motion along a line. And secondly, one of the eigenvalues is 0 and the other is negative. And for Hamiltonian systems, the eigenvalues always come in pairs, right? So for example, if you have one positive eigenvalue for a Hamiltonian system, you have to have one negative eigenvalue. And that's why you can never have asymptotic stability for a Hamiltonian system. If you have things in the left half plane, you also have stuff in the right half plane. So the rigid body is fine, it's stable, but it's not asymptotically stable. And similarly for other Hamiltonian systems. But the other nice thing about these non-holonomic systems is they can be asymptotically stable. And again, this is related to the fact that the Poisson bracket is not really Poisson, it's almost Poisson, or the Jacobiator is non-zero. And this is the sort of simplest example that really illustrates that. So it has this really beautiful dynamics. So any questions about that? Okay, so let me say something. So I want to say something more, and again, I'll talk about other integrable systems, but
just one. Let me.
Yeah.
I'm trying to sort this.
Formulate it, yeah.
So if you have a non-vanishing Jacobiator, right? I mean, this is in a sense the Jacobi identity is a statement about the Poisson bracket being a derivation of sorts on that algebra, right? So
Right.
if you sort it a different way, it looks like a product rule.
Yeah.
And so the statement, right, the notion that you break that product rule, can I understand this geometrically? And I'm coming from totally off field, I know, but can one think about, can one give this a geometric interpretation of sorts?
Yeah, so I mean, so the product rule is certainly part of it, right? You have the sort of Leibniz identity. So it's a little, I'd say it's a little more, so it's a little more than a product rule in a certain sense. But the geometric interpretation, so I mean, the way I think about it is, if you think of it on the Hamiltonian side, you have this two form which doesn't vanish. So that's sort of related to the product rule in a sense, right? So if you take, so normally you have, if you look at the Hamiltonian equations and you want to check that they preserve volume, you need the fact that, when you do that little computation, you need the d of the symplectic form is equal to 0. That's what makes the volume preservation work. And in this case, when you do it, you don't get d is equal to 0. So in that sense, it does kill a derivation. So it sort of blocks that derivation and things are not conserved. I mean, that's the sort of mathematical version of it. I mean, it's somehow, you know, it's the Jacobi identity and the fact that the symplectic form are closed is what's key to making things Hamiltonian. And people sort of tend to forget that, I think, when they look at Hamiltonian systems, they just think of it as, well, it's skew and therefore everything is nice, but that's not enough. So here things are skew, but they don't have this derivation, as you say, it's a derivation property. D of the omega is equal to 0. So I don't know if that helps.
Probably if I think a little longer, it will help.
Okay.
You're giving a starting point to think.
All right. So you know, I'll illustrate this more as we go along now. So here's the Euler-Poincare Suslov. So this is again one of my favorite problems. So again, it's very simple, but it illustrates this, and you can generalize it in lots of nice ways. So here again is the rigid body equations. So omega are the system angular velocities, I the moment of inertia. And now I put a non-holonomic constraint, which is just a linear combination of the omegas are equal to 0. So A dot omega is equal to 0. And you can now compute, again, the non-holonomic equations of motions by opposing the constraint on condition on the right-hand side. And you can solve for lambda, and those are the equations you get. And this is a sort of really beautiful set of equations of motion. And so I haven't got a picture here, but so the way you can think about this is, so it's non-holonomic because you're constraining these quasi-velocities, omega 1, omega 2, omega 3. And one physical representation of this is if you just took the rigid body and you stuck a rod through the rigid body with two blades on the end, and you put it inside a sphere, it tells you can't rotate about a given axis of inertia. So it might be along sort of one of the principal axes, it might be some other axis, but you're stopping yourself from rotating about a given axis. That's the constraint. And that turns it into a non-holonomic system. And again, it has sort of interesting behavior. I'll say more about that in a second. And so this is an example of what are called Euler-Poincare Suslov problems, where you put it, instead of put it on SO3, you put it on any group. And you have this general constraint that I've written over here. And the classical examples are the two examples I've just given you, this Chaplygin-Slay, which I just discussed, and the Suslov problem. So they go back to Chaplygin, 1895, Suslov, 1982, in the simplest setting. And the interesting thing here is that you want to check whether measure is preserved or not. So this is the general dynamics. You can write it in terms of momenta. Again, you can write it in terms of the structure coefficients that I mentioned earlier for the rigid body. And you want to check that whether or not volume is preserved. And again, it's a question you could ask. So for a Hamiltonian system, the volume is always preserved. For a non-holonomic system, it's sometimes preserved, sometimes not. So you ask the question of whether it has an invariant measure, and you can check that it's a condition on the group, that these equations are invariant if and only if the group is a so-called unimodular group. So the unimodular doesn't really matter too much here, but this is the condition for unimodularity. There's these conditions on these coefficients. And basically what it means is the divergence is 0, right? So it's pretty intuitive, really. But basically you want that, if you have a divergence-free vector field, it preserves volume. So Hamiltonian vector fields always preserve the divergence. Non-holonomic systems don't always preserve the divergence, and you can capture it in these sort of interesting ways. And then you can generalize what I just did. So you can look at these so-called Euler-Poincare Suslov equations. I have it on a general Lie group, and I have this condition, the constraint, which I impose by a constrained multiplier. And then you can check these things. Yeah.
Just another stupid question here. I'm just trying to connect to things I vaguely remember, right? This is the same condition you get to that makes sort of the square of the Lie derivatives, right?
Yeah.
The same as Laplace-Beltrami or something like this.
Oh, actually that I'm not sure about. You might be right. I'm not sure. I'll have to think about that.
You get on something you get naturally on Lie groups when you try to when you try to write this out.
Okay, yeah, I'd have to check. I'm not quite sure the connection with Laplace-Beltrami. It rings a bell. I'd have to think about that.
Yeah, let's take this offline, I think.
All right. Okay. I mean, you might be right. I'm just not quite sure off the top of my head. But anyway, this is the condition, at least algebraically. And so that tells you whether things are conserved or not. And so for example, to go back to the Chaplin-Slay, volume is not generally preserved. You get the supermarket type behavior. But if the center of mass is directly over the contact point, then the volume is preserved. And then it behaves like a Hamiltonian system. And again, if you think of the rolling penny, the center of mass is over the contact point. It behaves nicely. So volume is always preserved for that rolling penny. Here it's not preserved precisely when you have that sort of displacement of the center of mass. That's the physics of it. And it actually, in coordinates, it's also kind of nice. You can rewrite this. If you think of the angle, it turns out, in fact, that that condition, so for the Suslov problem, remember I had this condition, there it is, A dot omega is equal to 0. It turns out that the volume is preserved precisely when A is an eigenvector of the moment of inertia tensor. So if A is an eigenvector or an eigenstate of the inertia tensor, the phase volume is preserved. And if it isn't, it isn't. So that's kind of nice.
Sorry, just a quick follow-up.
Yeah.
You mentioned the rolling penny.
Yeah.
The center of mass is directly above the contact point. That's
Yeah.
true on a flat surface. What happens when the penny is going down a slope?
Yeah, so that right. So that would it still would be interesting. So the rolling penny down the slope would still be fine. It would have this kind of interesting behavior depending on its spin. But it would still be volume preserving, I believe. And the same is true for the falling rolling penny and so on. So it sort of depends on the internal, depend on an internal sort of asymmetry to give yourself volume, the lack of volume preservation. So I'll indicate that again with another example in a moment.
Okay, thank you.
I mean, that still has interesting behavior though. Yeah, let's see. So, so we can extend this also to internal variables. So I mean, it's nearly 9 o'clock. So what I could do, so I don't know how I don't want to sort of extend my time. So I want to say something. I could say something about the general Hamel equation, or just illustrate this by an example, I think. So should I just talk for like another 5 or 10 minutes and then stop? Does that work, or should I?
Again, we will take as much time as you're willing to give us. This is fantastic. So
All right. So I hate overstaying my welcome, but okay. Let me take a little more time. So I just want to say a little bit more about integrable and non-holonomic systems, and then the quantum case, since you asked me about that, and then I'll stop.
That'd be great.
All right. So I'll take a few more. So the Hamel equations. So I'll flash them up here, but basically the Hamel setting is also very nice. Is what you do. It's sort of a generalization of like the rigid body. So what you do is you choose coordinates that are adapted to the system. So for the rigid body, or the Chaplin-Slay, for example, the natural coordinates you might take instead of theta, phi, and x, y, or whatever, you might take coordinates that are adapted to the body, say along the direction of so along the blade direction or perpendicular to the blade direction, something like that. And that's what the Hamel is. So instead of taking your standard coordinates, say theta dot, phi dot, or whatever, you take non-trivial linear combinations of them. And that's what that equation at the bottom of this page is. So I take some sort of interesting combination of the coordinates and I try and write it in a nice way. And in particular, what you try and do is you write it so that the non-holonomic constraints are kind of trivial. So you try and change the variables so that basically the constraints are one of these combinations. And then all you're doing is putting that variable equal to 0. And then you don't have to do any crazy stuff with variations or Lagrange multipliers, and the equations just pop out. That's basically the Hamel equations in a nutshell. So you basically write the Q dot to some nonlinear combination of other variables, substitute it into the Lagrangian, and you see what you get. So these are sort of weird, as I've written here, non-canonical variables. So I won't worry about all the details. Let me just show you the final set of equations. So these are the Hamel equations over here. So this is written, so basically a special case of this would be the rigid body where the V's are the omegas, but you can write it more generally for any system. You take all these interesting linear combinations and in coordinates, let's see, you can do it. So yeah, I mean, that's nothing to do with non-holonomic. Those are the equations of motion. Then you do the Lagrange, then you can impose the constraints. And as I said, you can choose the variables so the constraints pop out really nicely. And again, sort of figure, just like the discussion we had earlier, a constraint basically is a subset of the tangent space. At every point, you're choosing a particular direction. So you choose a particular distribution that satisfies the constraints. You do Lagrange D'Alembert, just like I did earlier. and you end up with the equations that look like this. So these are the non-holonomic systems in the constrained Hamel form. And the constraints just come out to being putting some of the variables equal to 0. So basically, you've somehow did what I did earlier just by changing the velocities. You've changed the variables so that putting the constraints in, or at least enforcing constraints, is just putting a bunch of sort of, combinations of velocities equal to 0. So life is easy. And this is what the equations look like in coordinate form. And as you can see, it's sort of a little bit like the rigid body term. The first term here is sort of rigid body-like. And then there's a bunch of extra there's some extra things as well. But basically, it's got the flavor of the rigid body, and imposing the constraints is kind of nice. And you just need, it just goes here to n minus p, where you have p constraints. So you can just kill the constraints in a kind of nice way. So that's the point of the Hamel.
Sorry, before you go on,
Yeah.
just to continue, when one has holonomic constraints, one way of dealing with them is to explicitly solve for some of the degrees of freedom in terms of the others, and then apply the variational principle where all the variations are completely independent.
Yeah.
Is there a way with Hamel to, in a similar way, basically eliminate certain degrees of freedom and then be able to use a variational problem to solve for your equations of motion, even for a non-holonomic system?
Yeah, no, you could absolutely do that. Right. So again, I mean, so things would simplify a little bit, but right. So you could just do it in terms of the velocities. So yeah, so if you have a system constrained to a sphere or something like that, these Hamel equations apply perfectly well in the holonomic setting as well. And as I said, I mean, and the rigid body, for example, as I said, it's a case like that, right? So for the rigid body, you could do it in terms of Euler angles, where you'd have theta dots, phi dot, some complicated thing. But if you choose your variables, so doing the rigid body in terms of, the Euler in terms of the angular velocities, the body angular velocities, omega 1, omega 2, omega 3, is really doing what you're saying for a Hamiltonian system. So yeah, so even for holonomic systems, they're fine equations to look at. Absolutely.
Yeah, but I guess even further than just doing it as a holonomic system, but I mean,
Yeah.
the key difference in the usual variational sort of Hamilton's principle as treatment is that you can apply Hamilton's principle with holonomic constraints by eliminating some variables and then having all of your variations be completely free and arbitrary. And so then arrive at an Euler-Lagrange equation, set of Euler-Lagrange equations. And the difficulty with the non-holonomic constraints is that there's no obvious way, and basically from what you've talked about earlier, it's impossible to eliminate certain degrees of freedom because you can get anywhere in the phase space with a non-holonomic constraint.
Right.
But it seems like with these Hamel equations where the constraints, imposing the constraints implies that you just set certain velocities to 0. It seems like one would be able to construct a generalization of Hamilton's principle, that one would have a variational principle, variational action principle in the usual sense if you write the Lagrangian in terms of these Hamel variables and then remove some of them and then allow your variations to be completely arbitrary.
Yeah, you can sort of do that. No, you're right. So yeah, I see what you're saying. Yeah. So in fact, I haven't written that down here, unfortunately. But yeah, you can write down a sort of an analogous. You can write down the variational principle or the correct variational in terms of these Hamel type equations quite directly. And you can do that. And it's in a couple of the paper that I'm referring to here with Zenkov and Marsden. So we do that. You can write down the corresponding kind of non-holonomic variation principle in this Hamel form, and it is kind of elegant in the way you just suggest. Yeah.
Very good. Thank you.
So yeah, so that's in the paper if you want. It's this 2000. I think it's the paper I think I actually sent you. I think it's in there.
Okay.
Yeah, so here's a nice example of this, and this is a non-trivial, non-holonomic integrable system where we use the Hamel equations. So this is the Chaplygin sleigh with an oscillator. So you take the sleigh that I had earlier, the supermarket cart, and you just put an oscillator in the middle. So the interesting thing about this, it's really when we first looked at it, we weren't sure how this was going to behave, right? Because so what you do is so the mass is not you can think of the mass in its rest position as over the center of mass, in which case it behaves Hamiltonian. And then now it oscillates back and forth. So sometimes it's over the center of, so sometimes this little point mass on a spring is above the center of mass, and sometimes it isn't. So it oscillates back and forth. So the question is, what does this do? So it wasn't entirely obvious to us, but in fact you can, I don't know. So it's sort of half, it's kind of, it oscillates between Hamiltonian and not, if you like. Anyway, so you can show the flow is integrable, and the generic manifolds are two-dimensional tori just for a regular Hamiltonian system. So this is it. So here I describe it. You have a mass sliding in the direction of the blade. It's coupled through a spring. At the contact point, it oscillates back and forth. The phase space now is SE2 cross R. It's R for the mass, SE2 for the position. There's one shape in the sense that I described earlier, like for the falling cat. There's a shape which is just the distance to the contact point. It has 3 degrees of freedom. And this is the equations of motion, sort of written in this kind of, or at least this is the Lagrangian, written in this Hamel form, and you just want to compute what happens. So I won't go through the details, but this is what the dynamics look like. So you can see it's sort of an interesting combination, in fact, of spring dynamics and rigid body dynamics. So if you look on the first equation here, there's minus kr, that's from the spring. So the first thing is just a complicated version of the spring equation. And the last 2 equations are literally like the rigid body equations in the plane. It's sort of quadratic in the right-hand side. In fact, if you just freeze everything here, you'll see you get back the regular Chaplygin-Sleigh. So that's what the reduced dynamics look like, and you want to know what actually happens. So it's an interesting set of equations just to stare at. I won't say too much about it, but you can look at its relative equilibria. It has all sorts of symmetries, in fact, discrete symmetries, which I've written down here. You can change signs and flip things around. It has a lot of interesting discrete symmetries. And you can actually solve it. This is what the equations look like. You can study some of the solutions. And let me just show you, so I won't worry about them. But what you can show is that you get this interesting periodic behavior. The reduced dynamics is integrable on an open subset of the reduced phase space. The invariant tori are one-dimensional. The reduced flow is periodic. And this is sort of one of the trajectories. So this is the result. The generic trajectories are of the couple on the full. This is the full. You can look at the full phase space and the reduced phase space. This is the full phase space, quasi-periodic motions on two-dimensional invariant tori. And you get these wonderful motions for the blade point. So this looks like, if you remember, or maybe you don't, spirographs. I think they still exist. So these look like spirograph patterns. And so these are various initial conditions. And you can see it's got this, so for the Chaplygin-Sleigh, right, it just it just reverses direction and comes back to where it is, to where it used to be. So it flips and you get a cusp or something. But here, because of the oscillator and back and forth, you get these beautiful periodic patterns. So it's both integrable and it's got this beautiful dynamics. So I kind of like these. So any questions about that?
No, it's great.
Fantastically cute looking. Wow.
Yeah, I mean they are cute, and you can see you get these little cusps here as well. So each of these little things is like a little baby Chaplygin-Sleigh all strung together in a periodic way. I don't know. You can think about it like that. Okay, so that's kind of fun. Let me just so let me just end up with one thing. I just want to say something about the just about how you might quantize things. So this is related to non-holonomic systems as limits. So another question you might ask is a non-holonomic system a limit of a holonomic system? And in some sense, you might think intuitively it is, right? Because what you do with a holonomic system, you have say a contact point, and there has to be infinite friction, which of course is not physical. So infinite friction means you can't slide perpendicular to the contact point of the blade, or that you roll without slipping. But you could think about taking it as a limit of a strong force. So you have, say, friction, you let the friction go to infinity, and when the friction goes to infinity, you get a non-holonomic system. And in fact, that's sort of true. And it goes back to Caratayadori. He started thinking about this. So there's an interesting story that relates to this. Caratayadori claimed, interestingly enough, Caratayadori claimed you couldn't do this. So he thought about this problem and said, no, you can't solve it. In fact, you can do it. It goes back to Fufayev, Kozlov, Karapetyan. And the idea is you take a Rayleigh dissipation function, and which encodes the constraints. So normally you think of, Rayleigh dissipation function as a quadratic in the velocities. You take its derivative, and that gives you the dissipation. But you can take a nonlinear version of that, which enforces the constraints. And that's kind of a beautiful story. Again, for reasons of time, I'll skip the details, but you can show, for example, you can get the Chaplik and Slay that I just showed you here. So these are the equations of motion. You add for, so now what you do is instead of taking the constraint, you add for yourself a viscous friction force. You take the friction force to infinity. If you take the friction force to infinity, you end up with the correct equations of motion. So these are the Chaplik and Slay equations, again with now with their friction force. You take the friction force together to infinity, and you do get the correct non-holonomic equations. So that's kind of a cute story by itself. It comes from a sort of limit of the Rayleigh dissipation. So this is just taking the limit. But this is related to, so just to end up with, how might you quantize a system? Well, if you want to quantize a Hamiltonian system, what you're supposed to do, right? I mean, there are various ways of thinking about it, but is you replace the, you have a Poisson bracket, or you have a Hamiltonian structure, right? And you replace the Poisson bracket by the commutator, right? So you end up with, say, Heisenberg equations of motion instead of the standard bracket equations of motion. Well, we can't do that here since we don't have a bracket. And again, there have been various weird papers trying to do that. It never quite works. But here is one way you might think about it, which is to keep the system Hamiltonian. So how are you going to do that? Well, you think of yourself as having an external field. So there's an external field which kind of keeps the blade in the right place, right? So you have an external field which enforces the constraint, and and you can think of that, and that's another way, in fact, even of doing classical systems with dissipation, right? If you have, say, a mass connected to an infinite string, right? The mass oscillates back and forth. And if you add a dissipation, it'll eventually start to sort of stop oscillating. But another way to do it is connect it to a field. And say the simplest case is, and there's an interesting history to this as well. It's due to Lamb, which I've written about in some places. I take my mass, I connect it to an infinite string, and then the mass really acts like a damped oscillator. It sort of oscillates back and forth, and the string takes off energy to infinity, but the system remains Hamiltonian. And that's sort of the idea here too. So what you do is we take a we attach the system to some sort of field, and we take the limit of the field such that it enforces the constraint when the field goes to infinity. That's sort of the basic idea, similar to what I just did. So I take my sort of free Lagrangian, say for the sleigh or a blade, and then I take a limit and enforce the constraint. So that's basically what I do, and that is literally a way of enforcing the constraint. That's just what I did with a field instead of a dissipation. So I think of that Rayleigh dissipation as coming from a field. And then if I want to do quantum field theory, I do a similar sort of thing. Basically, I write down the Hamiltonian, and then I quantize the Hamiltonian. At least I quantize the system connected to a field, which I'm allowed to do since it's all Hamiltonian. And then I take the limit and I get the quantized sleigh. And that's sort of the idea. And it kind of works in some cases. So basically, this is what it is. This is the quantized sleigh. This is the Schrödinger equation for the quantized sleigh down to the bottom. So that's kind of a cute thing. That's the reduced equation. These are the eigenvalues. And but unfortunately, we're still thinking about this. It doesn't actually work in general. It only works for some constraints. So unfortunately, it's not a full recipe for quantizing non-holonomic systems. It works for certain constraints, not others. How you do this in general is still a bit of an open question. But nonetheless, there is a way in certain cases, like this one, of quantizing it by sort of thinking of the constraint as coming from a field and taking a suitable limit. So
what breaks when you try? So you say it doesn't work in general. So what are some examples of when it breaks down?
Yeah, well, so the problem is it's the Rayleigh dissipation function thing. You have to end up with something like this, and it's kind of hard to construct a field that gives you which we are unable to do, and I haven't thought about this just recently, but you're unable to construct a field that actually implements this non-holonomic Rayleigh dissipation function. So it's just coming. So this is quite a complicated function in general, and coming up with a field that implements this is the problem. but in certain cases, it's possible to do it.
But generically, you need to set up something that is dissipative. So you need a larger system in which to dissipate into, right? I mean,
Yeah,
system
exactly. I think that's exactly the way to think about it. Somehow you have to embed it in, just like I did here, so just like I did for this limit in this special case. You say here, so there's a 3-dimensional, so you have this, so for this Chaplik and Slay, I really have a 2-dimensional system, but now I enlarge it and then I take a limit. And you have to do the same thing there. So yeah, that's what you have to do. So it's kind of tricky. Yeah.
So you build up some sort of entanglement, but then you squeeze it away in one direction. That's
Right. Yeah, that's exactly how I think about it. Yeah. And there might be other ways to do it. So there are other people who try, so how do you quantize this? How do you, so quantizing a system in general is quite hard, particularly also if it's on a manifold, right? There's if it's in flat space, that's still an open problem, or a lot of people have thought about it, Bertrand Constant, how do you quantize? I mean, mathematicians love this. How do you quantize a system on a manifold? Not really that obvious. I think that's still an open problem. And then again, as I said, if you don't have a proper Poisson bracket, how do you quantize a system with this? So you could just phrase it as how do I quantize a system properly with an almost Poisson bracket?
Right.
That's an unknown question. So this is sort of one way to do it. You might argue it's ad hoc, but these fields are kind of nice, and so we've looked at other systems like this. So systems coupled to fields are interesting in general, right? And so there are kind of interesting things about the stability of systems as well. So just like here, you get these interesting stability problems. If you have a system that's stable and you couple it to a field, it also can go unstable. This is related, some other work I did with Jerry Marsden was what we call the problem of dissipation-induced instabilities. If you have a system, so for example, there's also interesting physics here. If you have something like an n-body system that's stable, if you want to prove the stability of the n-body problem, that's again an open problem, right? So if you linearize the n-body problem, again, since it's Hamiltonian, you'll get all the eigenvalues on the imaginary axis. But of course, that's not enough for stability, as we know, because it's nonlinear, so all sorts of crazy things that can happen. But if you add dissipation, you might wonder what happens. And what we did in the dissipation-induced instability thing is we showed that if you had, if the standard Lyapunov function treatment fails, the system's unstable. Then if you add dissipation, you can show it's truly unstable. So sometimes you think of dissipation as stabilizing things, but sometimes dissipation destabilizes things, and that's sort of an interesting thing, and it's sort of related to this. And if you want to do it in the Hamiltonian context, well, you can take your n-body system and you link it to a field. So if you had your n-bodies floating around in a field, then it's not really so obvious whether what's stable, even though all the eigenvalues might be on the imaginary axis, it could be stable or it could be unstable depending on how the field interacts with the system. So, I think fields interacting with these finite dimensional systems is kind of interesting by itself, and it's one way of thinking about these non-holonomic systems. Okay, so that's, I guess, I mean, I could say a lot more things, but I think I think I'll stop there, and I'm happy to answer any further questions. I was going to say a little bit more about how Hamiltonian systems, how the Jacobiator arises. One can say things like that, but I think I should stop here.
Fantastic. That was really amazing. Thank you. Questions at yeah, please.
I have a simple question. What is the distribution associated with a constraint?
Sorry, can you talk a little louder? Sorry, I couldn't quite hear that.
What is the distribution associated with a constraint?
Oh, right. Yeah. So the way I think about it, right, is a constraint is it's a relationship between velocities, right? So for the rigid body, for example, at least for the rolling penny, right, it was something like x dot equals r cosine phi theta dot, right? So it puts a constraint on the velocities. So then going back to what we were talking about earlier, so when I think about dynamics normally, right, I do think of dynamics on the tangent bundle. So for a regular Lagrangian system, there's the configuration space, And at every point, that's the tangent space, which is the set of all velocities, right? For the rigid, so for the rolling penny, it'd be theta dot, phi dot, x dot, y dot. And a distribution means that you just constrain the set of velocities. So instead of having the whole tangent space at every point, I just have a subspace of the tangent space. So those two constraints, say for the rolling penny, would cut out a two-dimensional subspace of the tangent space. And so so you can think of a non-holonomic system really as being, a system on the tangent bundle, but at every point on the tangent bundle, I'm only allowed a subspace of the tangent bundle, which can vary from point to point. And so that's the distribution, a subspace at each point. Does that make sense?
Yeah, that does.
We have a question on.
Yeah, Alexander, would you like to ask your question?
Thank you very much, and thank you for the very interesting talk, Anthony. Could I ask, when you define non-holonomic constraints, you restrict to linear in velocity, and I would like to know why at which point this linearity is crucial, and why quadratic constraints, for example, are not considered on the same level with the methods that you presented.
Right. So, yeah, I mean, that is a good question. So most, almost all mechanical systems have these that's just what we see, right? What we call they're linear or affine. But there are cases where they're not. So you could literally, I mean, there's nothing to stop you from putting a constraint of the form f of q dot equal to 0, nonlinear in q, some crazy thing. And you can write that down. So we've written some stuff on that, and other people have. So you just have to be careful again to get the right physics. Okay, so how you implement the constraints is a little tricky, but there's nothing wrong with it. And this is, there are these problems. They're so-called isokinetic problems. So for example, if you have for example, in some and this is actually related also to numerical methods. If you connect a system of particles to a heat bath, you can have the kinetic energy preserved rather than the full kinetic plus potential energy. So that's a non-holonomic. That's a nonlinear non-holonomic constraint. Like I have sigma. So an interesting system is sigma mi qi dot squared equals a constant, right? That is quadratic in the sense that you described, and you can and those are actually really interesting problems as well.
Perhaps,
I mean, so there's nothing wrong with that, and you just have to be a little more. You have to be even more careful that you get the right physical systems.
allow me to follow up on this, because you've now moved to a different example, but the penny that you showed in its original formulation has a quadratic constraint, and the fact that you can rewrite it into a linear velocity constraint is sort of a extra clever way of simplifying the system. But if you take the penny face on, as we would describe it in introductory mechanics lecture, rolling of a disk, then it would come out with the quadratic constraint in velocity. And would the methods that you've presented us work? Or do we always have to find a linear realization?
I think you have to find a. So I'm not quite sure what you mean. So what would be quadratic? So the penny. So the constraints.
If I have a three-dimensional system, then the velocity of the center of mass is a v vector squared. Sorry, it's v. Exactly, v vector squared equals r times omega vector, r squared omega vector squared. So that is the original relation between the velocity of the center of mass to the angular velocity of the disk.
Yeah. Well, I think
so.
Yeah. So I'm not quite sure I got the right answer to this, but in that case, I think, there's a combination. If you look at it in 3 dimensions, there's a combination of holonomic and non-holonomic. And, you can probably formulate it more generally, like if you just think of it in space, as you say, but I think of it on the plane. Once I'm on the plane, then I can rewrite it, as you say, in terms of these linear constraints. And then you have all this nice geometry. I mean, so there's an advantage to having it affine, which is, you get you've got this connection that I described, you've got the geometry and so on. So Yeah, you can reformulate things in lots. I mean, now I could see there might be an advantage, and depending on what you're thinking about, there might be an advantage of thinking about it some other way. But any sort of physics, if you think of a natural system, this is just rolling or sliding or whatever, a car or a robot or whatever, then they're all you can always formulate it in terms of these linear or affine constraints, and that has a nice geometry. There's this bundle geometry, which does a lot of things for you. But
Perfect. Thank you very much.
Yeah. Okay. Yeah.
Other questions from audience? I had two possibly related questions. So the first one is just for context with the holonomic constraint, and you mentioned this also very nicely. One can think about imposing the holonomic constraint as imposing an external force that constrains you to the holonomic surface.
Yeah.
Is there an analogous way of imposing, or has anyone thought about an analogous way of imposing an external force that constrains you to the non-holonomic constraint surface?
Well, I mean, I think, the multipliers do that. So I think, the point is you can't do it variationally, but to do the Lagrange d'Alembert, I mean, if this is what you're asking, you can think of it two ways, right? You can take, you write down the equations of motion, you take those delta q's, right? And then you can you can eliminate the delta q's or whatever at the end using the constraints. Or you can write down, the regular Lagrangian equations, and then you impose the forces of constraint on the right-hand side by Lagrange multipliers.
Right.
That is certainly okay, right? I mean, as long as you, sort of monitor where you're taking variations, or where it's variation and where it's not. So you can, so Lagrange d'Alembert you can think of as, just you're imposing, you've got the variations which have to satisfy the constraints, and you can use multipliers to do that, and those multipliers are forces. They're just forces that do no work. So absolutely, but it's not this. Obviously, it's the forces that do no work that appear in the equations of motion, but they're not forces that constrain you, of course, to a given surface. So, I mean, I guess that's the difference. They're not forces that keep you to a surface, but they are forces that impose the constraints in the dynamics.
I guess as you say that, what occurs to me is that in the holonomic instance, you can write those forces of constraint as the gradient of a potential, where the was the constraint surface itself, the equation of constraint itself. And the point is that for the non-holonomic constraints, you cannot write the forces of constraint as a gradient of a potential.
No, absolutely. No, I think so. And in fact, if you go back to Lagrange, if you look at Whittaker's book, for example, you'll see when he does, Lagrangian mechanics, right? So you can write it with, you can write in the forces on the right-hand side, just keeping things covariant. And there could be general forces, and in particular non-holonomic, if you like. And then when they come from a potential, you can sort of absorb them into the Lagrangian, and everything's Lagrangian. Yeah, so that's absolutely right.
Awesome. And then the last question, which is potentially a little bit related. Have you heard of the Dirac-Bergman algorithm?
I know about direct constraints. I'm not sure, and I've heard of Bergman, but I'm not sure what the Dirac-Bergman algorithm is. I've heard of both of them. Yeah, it's all right. Maybe you can tell me.
Yeah, so for some context, so in quantum field theory, when you have gauge theories like in quantum electrodynamics or quantum chromodynamics, the way that the modern way of imposing the gauge condition is as considering it a constraint, and using what's known as a BRST gauge fixing. And in a way that I don't truly fully understand, but is somehow explained in intimate detail in a book by Hainaut and Teitelboim, that the Dirac-Bergman algorithm, which is a way of starting from the phase space, Q's and P's, and saying you have Poisson brackets and you have constraints.
Yeah.
And you start with some initial condition that's on your constraint surface, and you look at the time evolution from the Poisson brackets, and then you see that your constraint is not necessarily satisfied as a function of time, so you start imposing extra constraints that basically keep forcing you onto the constraint surface. And all of physics has very, as far as I can tell, and my student Ben Bird, who's been thinking about this quite a bit, also who you've heard in asking questions, has just assumed that this algorithm works for non-holonomic constraints just as readily as for holonomic constraints. But what you've talked about so clearly in this talk is that you don't have a Poisson bracket structure for non-holonomic constraints.
Yeah.
And so if you want to figure out the equations of motion, there are some corrections to that Poisson structure that you need to include.
Right.
Which might lead you down the Dirac-Bergman hole.
Yeah, so that's right. I
Ways
think,
a lot.
yeah. No, I think so. That's a good question. I'll have a look. So that, right, the Dirac-Bergman. Right. So if you have Dirac constraints, right? So Dirac constraints derive from the fact that the Lagrangian is degenerate, right? So
This is along those lines.
yeah, exactly. So there's so I haven't talked about that here, but that is certainly interesting. But then, of course, there is a Dirac bracket, right? So in that particular case, there is a reduced bracket, and you can think about quantizing, et cetera, and there's Dirac's original book. So that's all fine.
Exactly.
Yeah.
But so I finally I dug into the original book, and as far as I can tell, all of his procedure presumes that the Poisson bracket structure survives,
right,
without any corrections. And so I think implicitly Dirac is assuming, I don't know if he understood this or not at the time, at least as far as I can tell, one is implicitly assuming that the constraints are either holonomic or integrably non-holonomic, and it would not work for a general non-holonomic constraint.
No, I think that's right. So, yeah, there have been a couple of papers related to this. I can think of I can try and think of it. But yeah, no, I think you're right. You see, so you have to be super careful. So if you're in that Dirac setting, they look very similar, whatever. But there are not. There are certainly nonlinear constraints on the velocities, but they come in a very special way, and then the quantization is fine. And I think that's true for the. I think it will be true with the field theory as well. So if it's truly non-holonomic, then you have to be very careful in just the way we described. Certainly, it's an interesting topic, and then of course in the Dirac thing you get these high order brackets. So yeah, I mean the constraints and so on. So you have to be careful. But yeah, so I think that's a really interesting question. I'll look at that book, and it just reminds me of something. There's something else. There was a lecture I saw a while back that tried to do something more with Dirac brackets and non-holonomic. I can't quite recall it right now. Let me see if I can track down anything interesting related to that.
That'd be amazing. And I'll send you the references that I have in my mind for this.
Okay.
Yeah.
Would be great. Thanks.
Amazing. Yeah. So thank you very much again.
All right. Well, thank you so much for the invitation. It was a lot of fun talking with you all.
This is fantastic. This is really, really great. So thank you.
Yeah, I am also not annoy you from my end. Thank you. Thank you again.
Okay. All right. A pleasure. Thanks very much.
Bye.
Cheers.
Bye for now.